In this example, we'll be looking at how to analyze a beam where there is a lateral torsional buckling possibility as well. So we'll be trying to find out the member moment capacity along with the member section capacity as well. So in the question, what it is given is that we have 460 UB 67.1 universal beam section, and as you can see here, we need to find out the maximum design bending moment capacity for this beam. And the beam is subjected to the uniform bending over a span of 3 meters, and it is a simply supported one, and it is fully restrained at the supports against lateral deflection and twist rotation. So it's a fully restrained at both the ends, but unrestrained against the lateral rotation. So it can rotate in a lateral, so there can be some lateral rotation at the ends, but it is fully restrained against lateral deflection and twist at both ends. The load is acting within the segment and on the top of the flange as well. So these are the conditions given here, and we need to find out the design bending moment capacity. So if we look into this beam, so it is a simply supported universal beam section, and it is loaded on the top, and we need to find out what is the design bending moment capacity. So what is given is that both the ends, it is fully restrained. So it is FF at both ends, and there is no restraining in the middle. And the span length is 3 meters, as we can see here. The span itself is, and if you look it from the top, there can be some lateral rotation in there. So let's analyze this beam, and let's find out the member moment capacity of this beam. Now, as we do always, so first we have to find out the section moment capacity, and then we use alpha S and alpha M factor to find the member moment capacity. So the given section we have is 460 UB 67.1. Now let's first find out the nominal section moment capacity. It is bending about the x-axis, so we write it as MSX. And the nominal section moment capacity about x-axis, which is the stronger axis, is yield stress of the material in the section multiplied by the effective section modulus, which is ZEX. This is because the beam is bending about the x-axis. Now we have to find out the FY, the yield stress of the section. Let's have a look at this one steel table where we have the section properties. 460 UB 67.1. The yield stress of the section is 300 megapascal for the flange and 320 megapascal for the web. So we'll be using the smaller one of these yield stresses. So for us, we'll be using 300 megapascal as the yield stress. And also we have ZEX for bending about x-axis. We have effective section modulus about x-axis is 1480 as well. So this is from the universal beam properties table. So let's write it down. So Fy, the smaller between the flange and the web, we have is 300 megapascal, and the effective section modulus, which is ZEX, is 1480. Now again, the effective section modulus takes into account and the compactness of the section as well. The local buckling is already incorporated in it. So therefore, the nominal section moment capacity, which is MSX about x-axis, is Fy multiplied by ZEX, and putting the values. So this comes in Newton millimeter, and if we convert this into kilonewton meter, it will come as 444 kilonewton meter. Now, once we have the section moment capacity, we can proceed to find out the member moment capacity as well. So, which is denoted as MBX. We have two factor alpha S and alpha M, slenderness reduction factor and moment modification factor multiplied to MSX. Now we have to find alpha S factor and alpha M factor. So again here we have alpha S is a slenderness reduction factor, whereas alpha M is the moment modification factor. And MSX is the nominal section moment capacity about X, which we just found out. Now, so let's look at how we can find alpha S and alpha M. Let's first look at finding alpha S. Now, to find alpha S, first we have to know what is the effective length, which is KT multiplied by KR multiplied KL multiplied by KR into the length of the beam itself. So let's write it down. So this is given in the equation. If you look in AS4100, this is the equation that we have for the effective length. So it is in clause 5.6.3. Supported over the span of 3 meters, and both the ends are FF condition, that is fully restrained at both the section, and there is no intermediate restraining. So it is the length itself is 3 meters in this case. So we have the length here as 3 meters. So there are no intermediate restraining. So your overall length of the beam segment is 3 meters. That is overall length itself. Now, to find the KT-KL factor, we have to look into AS4100. So KT is again the twist resisting factor, which we can find out from AS4100, as you can see here. So KT is a twist restraint factor given in table 5.6.3a. So let's have a look at it. So for KT factor, we'll look at table 5.6.3a. Now we can see that for FF condition, fully restrained at two ends, KT factor is 1. Right? We'll take it from 5.6.3a. KT is 1.0. For fully restrained FF condition, fully restrained, we have KT equals 1.0, and it is coming from table 5.6.3a. Now the second parameter that we need is the KL factor, which is obtained again from AS4100. Now KL factor, which is the load height factor, is given in table 5.6.3b. Now our load is acting within the segment, right? So it is within the segment, and also the load is acting on the top flange itself. Our case is fully restraining case, so it is 1.4. Now coming from table 5.6.3b, KL factor is 1.4. Because the load is within the segment. It is a FF condition, fully restrained in both the ends, and also load acting on so the load is acting on the top flange as well. So KL is 1.4, which is again from table 5.6.3b. Now the third factor that we need is KR factor. So let's have a look at the KR factor from AS4100. So KR factor is a lateral rotation restraining factor. So lateral rotational restraining factor, that means if you look from the top view, so this is your beam. It has FF support, yes, FF restraining, but the beam can still rotate in a lateral direction, right? So there is still, the rotation can happen. So there is no lateral restraining, rotation restraining in there. So in this case, we do not have lateral restraining, lateral rotation restraining, so it is none. And we the restraint arrangement is FF, both of them FF, so it is 1.0. That is the worst case scenario. So it is 1.0 here. So we are taking KR factor as 1.0 because we have FF condition and no lateral rotation restraining. So that is coming from table 5.6.3c. Now with that, we can find out our effective length. KL is 1.4 and KR is 1.0, and your overall length of the beam is 3 meters. So that means we have effective length as 4.2 meter, which is 4200 millimeter. Now, once we know the effective length, we can find out the reference moment which we need for finding alpha S. So finding reference moment M naught. Reference moment M naught is again given from AS4100. So if you look into the AS4100 here, so clause 5.6.1.13 gives us the reference moment equation. So we can find out the reference moment equation from here. So the parameters that we need in this equation are Iy, which is the moment of inertia about y-axis, which we can obtain from one steel table. Similarly, we need the Young's modulus of steel. We already know that this is 200,000 megapascal. And we need G, shear modulus of steel, which is 80,000 megapascal. And we need J factor, and we need IW, warping constant here, and effective length we already have as 4200 millimeter. So let's go about and look at our one steel table to find out these parameters for our case. So as you can see here, our section is 460 UB 67.1. So the parameters that we are interested in here are, first we need Iy, which is 14.5 into 10 raised to the power 3. We also need J, that is a torsion constant, which is 378 into 10 raised to the power 3. We need IW, which is the warping constant, 708 as well. We need to find out, we need to use this one as well. So all of these properties are taken again from the one steel table. And now plugging it all of them back, and if you calculate M naught, just plug in the values. Remember, LE you have to put in millimeter as well. So put the LE in millimeter as well and just plug in back the values. So we get M naught as 421.4 kilonewton meter. So plugging back all the values, we get the reference moment as 421.4 kilonewton meter. With that, we can now find alpha S, slenderness reduction factor. So alpha S, or slenderness reduction factor, is given by AS4100 again. So let's have a look at AS4100 here. So the alpha S is given in by this equation, as you can see here. So that is what we have for alpha S. So we just plug in back in this equation and we find the alpha S factor from there. So it is 0.6. MSX is the nominal section moment capacity. M naught is the reference moment that we just calculated. So if you plug in the values, we get alpha S as 0.584 here. So we now have the slenderness reduction factor. So the next thing that we need to find is alpha M, which is the moment modification factor. So let's go and find out the moment modification factor, or alpha M. Again, alpha M, the moment modification factor, depends on the shape of the bending moment itself. It doesn't depend on your cross section. It's based on the shape of the bending moment. Now we have a simply supported beam with the uniformly distributed load. Over the span of 3 meters. So that means our bending moment shape is parabolic, like this one. So we need to find out alpha M for this bending moment shape from the table. So let's have a look at table 5.6.1 to find out what is alpha M factor for this bending moment shape. So look at AS4100 here and table 5.6.1. So in here, in the table 5.6.1, we see that our case is very similar to this one, except that the beta M is 0. So this parameter is 0. So if we plug in there, this bending moment shape is very close to our case. So we plug in beta M equals to 0 in this equation. So in this equation, beta M equals 0, we get alpha M factor here. Because there is no moment at the end, that means the beta M is 0 in this in our case. So because there is no moment at the end, so putting beta M equals 0, we get alpha M factor as 1.13 in this equation, right? So this is from table 5.6.1, and we looking at the bending moment shape, we have the beta M equals 0 because there is no end moment, so it is beta M is 0. That when we put beta M equals 0, we get alpha M equals to 1.13. So we have alpha S and alpha M. Now we can find out the nominal member moment capacity. So alpha S, alpha M, and nominal section moment capacity. So we have all of this parameter. Alpha S we found out as 0.584. This is the slenderness reduction factor. And the moment modification factor we found as 1.13. And the nominal section moment capacity is 444 kilonewton meter. So that gives us our member moment capacity as 293 kilonewton meter, and of course this is critical one compared to the section moment capacity. Therefore, the design moment capacity of this beam is the smaller of the two, that is phi mbx in our case, which is phi is the strength reduction factor for steel 0.9. This comes out to be 263.7 kilonewton meter. Now that is our design moment capacity of the section, taking the lateral torsional buckling into account.